Hello, this is Adam Van Etten from InQtel Cosmic Works, and today we'll be discussing city-scale road extraction from satellite imagery, something we call CRESI, which is a way to extract detailed road networks directly from imagery, and we'll be discussing how to do that just on a CPU, in this case, my MacBook Pro. So why do we need to tackle this problem? Well, the central premise here is that we can use a lot of help in accelerating mapping. In this case, the example that we like to use is after Hurricane Maria, it took months to relabel roads and buildings for Puerto Rico with a dedicated team of thousands of volunteers. And this was a commendable effort and something that we celebrate. But if we can do this faster than 2+ months, that would be very helpful. And the premise here, right, is satellite imagery is something that might be able to speed this up greatly. So why can't we just use current techniques? So rapid extraction of road networks and key routes is critical in dynamic scenarios, such as disaster response. This is something that we'll go into more later in the intermission period after we get into the demo. But I think that's probably not a controversial statement. There are some commercial approaches that address this. There's a number of challenges here. One of the principal challenges is that these networks are often outdated in dynamic scenarios, such as disaster response, where the road might be washed out or there's flooding or something like this. Academic approaches have started to tackle this more and more, which is very exciting. But these often just present like a segmentation mask, so just which pixels are road, which pixels are background, which doesn't really help you solve some of the routing problems. You can see this on the right here. And then if you do get a road network, often these don't have any road properties, so you can't do true optimized routing because you need those road properties to do this. So this is the motivation for why we're tackling this problem here. And so why do you need these road properties, right? Optimal paths are rarely the shortest geometric distance, right? So on the left here, what we're showing is that routing based on shortest distance gives you this path, but if you want to route based on time, which is usually what we actually care about, right, shortest time, it's a very different path. That's what we're showing on the right, of course, and so you need some estimate of travel time or speed limit or safe travel speed for these roadways if you want to do true optimized routing, in which you probably care about, which is time. So what data are we going to use to try and tackle this problem algorithmically? So SpacedNet is something that has existed for a few years now. It's a nonprofit LLC managed by Cosmic Works, dedicated to accelerating open source AI for geospatial applications. And we've focused on foundational mapping to date, mostly buildings and roads. There are 9 partners that are part of this, so this is definitely a team effort, something that would not exist without all these partners. And we're excited that we keep adding more over the years. So there's a pretty good data set out there now. This is a free and open source data set available on AWS. And we have a number of cities around all over the world in this data set. In this case, we actually have 8 cities we're going to use for training and or testing here in Khartoum, Shanghai, Las Vegas, Paris, Moscow, Mumbai, San Juan, and then Dar es Salaam. In these cities, we have foundational mapping labels, building footprints, and then road network labels and features. So again, this is the actual road vector that we can build into a network, along with features like number of lanes. That's some pixels on the side, pretty images. To kind of spur use of these labels and this data set, there's been a number of challenges, 6 to date, with the 7th in the planning phase for launch in the autumn of 2020. And we'll focus in this video on SpaceNet 3 and 5, which were the ones that looked at road networks. So SpaceNet 3 was just looking at the routing piece from just a geometric standpoint, just to get started. And then SpaceNet 5, which finished, that's fall of 2019, looked actually the travel time piece. And so that is this work then we're building up a network.
He's done a podcast before, and he did a great job.
There's a little more detail about SpaceNet 5. As with all the SpaceNet challenges, we tiled the images into small chips that are a little easier to handle. And then also the road labels. In this case, we build out a training mask categorized by the speed limit of the road. And then we challenge people to try and pull out the road network with travel time estimates for each roadway, so you can use this for optimized routing. So as with all the SpaceNet challenges, the output is a number of open source algorithms that we put up on GitHub. So we have one baseline algorithm and then 5 new open source algorithms. So if you look at this plot on the right, you'll see that the winning algorithms, these are the top 5, all scored a tiny bit better based on the apples metric, which we'll talk about more later, than the baseline, which is the Cressy baseline in the red diamond. The upside of the baseline was it's much faster. So it's far to the right on this plot, meaning it's a little bit faster, a little less performant, but in this case, since we're just running on a CPU, we'll stick with the Cressy baseline to show how quickly we can do things just on a laptop. So beyond just talking through slides, we'll actually show a demo of how to run this, again, on this laptop now. This is just a MacBook Pro. And we have this up on GitHub. And there's just a few commands to run to get started. This is all detailed here in part 1 of the tutorial. But we'll go through the steps now, just run a few commands and get that fired up. So if we run a Docker container, is spun up already. Just attach it. All right, so this is just the Docker container that comes with the Cressy GitHub. So all we need to do now is to open up a Jupyter notebook for this, and then we can run the tutorial in a Jupyter notebook, which is a pretty easy step. So we will open up this notebook. There we go. And here we are. All right, so this is the notebook. Again, this is up on GitHub. And here's some of the intro that I already provided in slides. But let's get into the meat of running this algorithm. So we'll just make sure we have our path set correctly. Here we go. And so all the model weights and the testing data is up on the S3 bucket that is SpaceNet hosts. All this data is free to download. I've gone ahead and downloaded it already just to save a little bit of time, even though this is a pretty quick step. But once we download it, what we're going to do is we picked Dar es Salaam for this example. And the reason being that there's no training done on Dar es Salaam. So this is a brand new city the model has never seen before. And so we're going to see how well we can extract the road network from a city that is not represented whatsoever in training. For this case, the whole point of Cressy is pulling out road networks at scale, so we can do any size we want. We're going to scale it down a little bit just to speed up testing and ease visualization. So this is just a step here to take this large image of the entire image of central Dar es Salaam, cut it down a little bit to make it a little bit smaller. So again, we start with an image that's about 50,000 pixels on the side. We're just clipping it down to something that's about 10,000, 12,000 on the side. This is obviously pretty quick to do, and I'll let that run. The output of this is this multispectral image chip. I won't go into too much detail on all the pre-processing, but one thing that the SpacedNet partners have been pretty careful to do is to provide the raw imagery, not just the kind of rescaled and prettified versions that you often see published, but the raw imagery, which means it's a lot easier to reproduce the work because you don't have these maybe opaque processes to provide pretty images. And so once we have this clipped, we're going to just take this raw image and then make it an 8-bit RGB image. So this reduces the size and makes it a little more tractable again. So that's what we're doing here. We're just converting this multispectral test data, so it's 8-band from the satellite. We're just taking the red, green, blue, and this is what we get. So this is our test image over Dar es Salaam here. Let me just make this a little bigger. There we go. And we're at about 12 square kilometers. So it's a decent sized image of Dar es Salaam. Cressy runs with just a config file. So the only thing you should have to do is make sure the paths are set correctly. In this case, they should already be set, but let's just check that. All right, so this is our config file that tells the algorithm different variables. These should all be fine. Now, the first step of this algorithm, there's multiple steps, is the actual deep learning aspect, right? So the first step is to run the segmentation mask to pull out road predictions. We will do that here. And this eval.py script does that, pointing at the right config file. So here we go. We're taking this large image. We have to slice it down first because you can't just shove a large image into a GPU or a CPU. It's just too big. So slicing it up first, and then we'll run it through the deep learning model. In this case, we picked a ResNet 3.4 architecture with a UNet backbone, something that we've seen good success with both internally and different challenge participants. So we're slicing it, then feed this into the model. We use PyTorch, as many people do, and then we'll kick off the testing of the model. Remember that we don't have to do any training here because the model weights are up on the S3 bucket, and so that's something you can use to start. So here we go. Here's the model architecture. We'll just print it out, and then we'll start running things through. So you'll see something like this if you're running it yourself. Should take usually between 12 and 15 minutes on this laptop. And if you can see that it's hammering away I'll just leave this up for now, give us an idea of when it finishes, because we'll let this run in the background, and then go to a bit of an intermission, because this will take, again, maybe 15 minutes to run, which isn't too bad, again, since I'm not using a GPU. And then we'll return at this point to the PowerPoint, and we can go through a little bit more of the motivation behind this and some of the details that we kind of glossed over at the start because I wanted to get this training started. And so there are a lot of applications of this, right? We've all used Google Maps, I'm sure. It's a great resource. And this kind of approach isn't designed to replace something like Google Maps. But again, there are cases where you don't have an up-to-date map because of dynamic changes, and something like the Cressy approach or other SpacedNet algorithms or some of the academic approaches, right, really could help. And so there's plenty of applications both in the government, civil, nonprofit organizations, etc., which can help. We're pretty interested in seeing how this could apply to autonomous vehicles, right? You need a hyper-accurate map that's up to date if you want to do autonomous routing. And with this automated pipeline, right, the hope is that something that you could just kind of run quickly and easily, even in the case of really changing difficult scenarios. So a little more background into kind of some of the things that are currently being done in academia, and some pretty impressive work here. And some of these just stop at a segmentation level. So see pretty good scores from some of these algorithms. On the bottom, you see a subset of some of the more recent and more impressive work, and even back in 2010, right? The bottom right. So this is not new to pull out the road masks. The problem here is that if you just evaluate based on pixels, you can get very good scores, and it's a good first step, but it's only a first step because you can't actually use this for routing. And to illustrate this a little better, here's a toy demo that we've kind of cooked up to show some of the issues with this. So on the left, say it's a ground truth road network, and on the right, in the orange and the blue, you see two different proposals with a couple of the standard pixel-based scores here. And in the middle one, in the orange, what you see is the widths aren't quite correct, so you get mediocre scores of IOU of say 0.69. Whereas on the right, this proposal, the widths are correct, and so you get a much higher IOU score. The issue here, of course, is if you want to do routing, this gap in the network in the blue is really a problem. And so this metrics to just measure pixel values really aren't what you want. You want something that actually is getting to the actual graph structure. And so something that we did for SpacedNet 3 and then adapted for SpacedNet 5 was end up developing a new metric we call apples for average path length similarity. And the gist here is we're looking at the difference in optimal routes between points of interest. And that is our measure of how well we reproduce a graph. And so you'll see these two graphs here on the top right. The ground truth graph, you see this yellow line going from the green to the red. But then your proposal graph has a different route because you've lost some edges. And so you have this different path. You do this for all the different paths of interest, sum it up, and you get the measure of the apples score. And so what this does, among other things, is that if you miss a node or an edge that's very central to the graph, has a high centrality, you get penalized heavily. Whereas if you do, say, a pixel-based evaluation, all pixels are weighted equally, and so you don't have a sense of if this intersection is really important to the graph or is it just a cul-de-sac. And so that's something you get out of something like a graph theoretic metric like apples. So just kind of to jump ahead a little bit, or maybe getting ahead of ourselves, but again, we got some time while the model runs, is just to show how this method compares with some of the other academic approaches. And here we're showing, in this case, New York City. So this is actually a different data set as well. So the model actually transfers pretty well to not just SpacedNet imagery, but in this case, this is just Google imagery. And on the left, you'll see Road Tracer, which was a pretty interesting approach to pull out road networks. And there's some issues here, right? You're missing some of the roads. You have roads in the water. And then our approach on the same data, these two algorithms are trained and tested on the exact same data. So I think this is a pretty good apples-to-apples comparison. And in our scoring, we'll see a significant improvement with this method over some of the other methods that are out there. So there's also the kind of commercial and open source space, right? We mentioned, of course, earlier, Google Maps is one great option. OpenStreetMap, Apple Maps are also options. Those have a lot of manual labeling, actually, kind of behind the curtain, so that can be a time issue. Road locations are often inferred from mobile phone tracks, which is a great option if you can do it. But if you don't have cell coverage, it's a rural area, or cell phone networks are down because of a disaster, et cetera, this isn't going to work very well. And solutions data are often proprietary, which obviously can impinge on your ability to deploy such things. OpenStreetMap is a great resource. We're very supportive of it, and often provides the only really decent network of an area, but it's often incomplete. So on the right, you'll see the top right, there's a missing road through the middle of this image. On the bottom right, you'll see buildings and roads. So road going through a building, which is an error. So this does happen in OpenStreetMap. And so it doesn't mean OpenStreetMap's not extremely useful, because it is. It's just incomplete. And so something that can quickly pull out roads is something that can be very valuable as you try to map areas of interest. And so here's just a kind of driving home some of the issues with OpenStreetMap. So this is OpenStreetMap labels for Shanghai, which is one of our cities in SpacedNet. And so there's decent coverage here of the actual roads. This is the lines on the right. But then we colored by the max speed tag. And blue means there's no recorded speed. And so as you can see, the vast majority of roads here have no recorded speed. And so this makes it difficult to guess at the best route, right? Because you don't have any metadata for the road to figure out, should I go on this highway or just on this surface street? Another thing with OSM is we did a comparison with the SpaceNet labels versus OpenStreetMap labels for the same exact area, train the exact same model, and then look at prediction scores for that. And the long story short here is that we saw a significant boost in performance when using SpaceNet labels versus OpenStreetMap labels. So there's a number of reasons for this. One just being that the labels and the imagery are better registered for SpaceNet, and I think just more attention paid to quality assurance with SpaceNet. So what this means is there's still value in really high fidelity labeling, even for places like this example is in Las Vegas. So something you'd think would have very high fidelity labels, you can still get a better performance if you really put a lot of effort into high quality labeling. So we'll go a little bit into SpaceNet 5 challenge. You kind of glossed over this earlier. So again, we kind of posed this challenge to competitors, where we said, all right, we're going to give you some images, train a model. Can you pull out the road network and give us an estimate for travel time? We use the Apple's metric for this, as we mentioned earlier. In this case, we're looking at the time between nodes of interest, right? Not just sort of distance, but actually time, something you can do since this metric is fairly flexible. So here's the top 5 submissions, along with the baseline, our Cressy baseline. And what you'll see from this highlighted column is pretty minimal spread in scores, right? So just about 3-4% difference between the top 5 scores, including the baseline, and but much different approaches for the segmentation models underneath, right? So the baseline uses one model, whereas some of them use up to 15 different ensemble models, which can give you a slight bump in score, but there's a huge cost in terms of inference speed. And so that's, again, why we usually stick, in this case, we stick with the Cressy model. A few takeaways that we found interesting. This is just a bit of a teaser for things that might be of interest in terms to dive in deeper, that we found out from SpaceNet 5, which is we had these training cities, and then Dar es Salaam, right, was held back. So no one knew what the final test city would be. So there was no training done on that city whatsoever, including with the baseline model. So that the goal was to see, can you build a model that does decently well on an unseen geography? And again, this is a little of a teaser to what we're hoping to show when the training or the testing is done. But what we saw is that the red bar here, which is Dar es Salaam, is not significantly below the other cities. And so we see successful model predictions in new geographies. And there's a number of reasons to this we don't have time to go into now, but that's pretty exciting, because you often hear that, like, you need pretty much exhaustive coverage of different areas to have a good model that will transfer. In this case, that's not necessarily true. With the multitude of training cities, in this case we use 6, in SpacedNet, looks like you can create a model that does decently well in an unseen geography, which is pretty exciting. A couple other things that were interesting kind of takeaways from SpaceNet 5 is, so there's not a huge variance in score here, as we noted before. So the purple is the final total score, so you can only about 3-4% difference between all those top 6 here. But there's a significant variation in scene level performance. So if you look here in this, say, both the top column, the top row and the bottom row, this is the same scene from all of those different algorithms. And there's quite a bit of variation here. And so what we see is that even though the aggregate scores are pretty close, if you look at small, like neighborhood level predictions, there's a lot of variance. So that's pretty interesting to be able to quantify that. So this is another way to just show that that we're looking on the x-axis. This would just be the chip ID, and then the y is the Apple score. So the point here is there's quite a bit of scatter. So there is quite a bit of variation among all of the different proposals, even though one thing we didn't really mention earlier was that all of the top submissions, the top 5 here, use a similar approach to the baseline model, the Cressy model. There's difference in the actual backbone neural network architecture and some difference in post-processing, but the general approach was similar. And we'll get in that general approach a little bit later, the post-processing steps after the testing is complete. So this is just to reiterate once again why we picked for this demonstration the baseline Cressy model, because again, inference speed is far faster than the winning algorithms. So let's go back and see how we're doing. All right, so we're getting close, just a little over a minute left in the first step. So this is something that, again, right in this case, about 15 minutes, 16 minutes to complete. Not too bad. Inference speed on a GPU would be 20 times faster-ish. If you use multiple GPUs, it'd obviously be even faster than that. So this is something you could speed up, but even the ability to run on just a laptop, in our estimation, was pretty exciting. We weren't sure it would work, but 20 minutes isn't too bad for 12 square kilometers in this case. And we included here in the notebook some links to some of these other blogs with a lot more detail than we've provided here for some of the lessons learned with SpaceNet. And I think some of these were also found in previous SpaceNet challenges, say looking at buildings, where there's a lot of nuance to these outputs, which in our estimation is pretty interesting, because just taking the best performant model is often what people want to do from challenges, but there's some more nuance there where the trade-off of speed versus performance and things like how you actually structure your metric can really be important to figure out how and if you should even deploy these models to use them for something like OpenStreetMap augmentation in areas where there isn't great coverage. All right, so we're down to the final image chip here, and we'll just, once that's done, then we can proceed on with the tutorial. Wanted to run this in real time just to show that like we're not cutting things and clipping to make it look faster, but there we go. There's the entirety of the deep learning aspect for Cressy run on a laptop, and in this case we had a time of around 16 minutes. All right, so let's continue on with the tutorial. So the output of this first step is a multi-class prediction mask. So we'll run that and plot it. Here's what we get for an example So in this case, we used 8 different channels. Each channel corresponds to a different speed. So channel 0 would be 0 to 10 miles an hour, channel 1, 10 to 20, et cetera, et cetera. So we're trying to predict which roads are seen at different speeds, and then there's an aggregate channel just showing the entire road network for that image chip. So this is a good start. This is what we did for SpacedNet 3 and 5. But if we want a larger network, something like the of Dar es Salaam, we have to stitch it back together. This is something that we've implemented. Originally something we called Basis. We've integrated it to Cressy, where pretty simply we take all these different chips, stitch them back together, normalize them, and then we get a final mask. So we'll run that. Again, in this case, we have 90 different image chips covering our 12 square kilometers. We will let that run, and then we should get a final prediction mask. Saving is often the slowest part just because we have large files here. Something that could be optimized clearly if you had a little beefier system than a MacBook. There we go. And then we'll plot the output here, which in this case, we're just plotting the aggregate mask. Here you go. Here's our road mask for the entirety of this unseen region. So again, you could stop here. This is a decent prediction mask. So some algorithms do. We have a few more steps to go because we want to actually get down to the actual network, not just the pixels. So what we do to do that is there's some cleansing of this network that we showed above here. And then we skeletonize the network, which is kind of what it sounds like, and then render that skeleton into a graph. I won't go into all the details here. I'll just run it. And what we'll get out is the skeleton of the network. It's an intermediate step where we just print this to a CSV so that you could score with the SpaceNet 3 methodology. And that can be skipped, but in this case, we just have the CSV. Here we go. Here's the edges of the predicted graph. Oh, I ran that twice. Well, the good thing it's quick, and then we'll just show the output. There we go. So we just get a CSV with different line strings. The next step is to actually include the geographic information. Again, it's something you wouldn't necessarily have to do if you're just submitting this to a competition, but the actual lat long and the coordinates are important if you're trying to actually deploy this. And let's get rid of this. And so this function here reads in that CSV and then takes the geographic information encoded in the GeoTIFF, the image file, and pulls out the coordinates of each of these edges, the graph edges and the nodes, the intersections. This is actually pretty slow because we're doing it for everything in the large graph. And so we multi-threaded it to speed it up a little bit. And we'll let that run. And we should get out a graph with geographic coordinates for all the nodes and edges. So there we go, computing geocoords for the edges. And it should be done in just a few seconds. There we go. I've left the images in here so that it's easy to see on the notebook, but the images that show up below are being re-rendered, right? So we're not just saving things. Here we go. So here's the actual graph that we've predicted with obviously the nodes in blue and then the edges in gray. The final piece is we want to actually get the speed of each edge and an estimate for the travel time. So what we do is, remember we had a multi-class mask, 8 different channels. Each channel corresponds to a speed range. So we can use these multiple channels to to back out the inferred speed for each edge. And that's what we do here in this next script, the infer speed script. This is quite quick, since we don't actually have to like compute coordinates or anything like this, no coordinate transformations. We're just looking at the different channels. So we're running that now, and there we go. So now we have a graph that has speed information in it. So let's explore this a little bit. So we'll plot the output colored by speed. Here we go. In this case, red is faster, yellow is slower. For this region of Khartoum, or of Dar es Salaam, I should say. And let's also look at this graph overlaid on the original image, which is what we're doing here. And here we go. So starting with nothing but an image, this is what we get for this region of Dar es Salaam. We're overlaying the roads or the original image. So that's a good thing to have. We now have a map of this region, but ultimately, right, what we want to do is to compute routes, optimal routes. So that's something that's actually pretty easy to do once you've got all this information from this algorithm. So first, we'll just build up a data structure of all the node locations, and then we'll say, let's pick kind of an area, just kind of randomly picked our assets to be here, along here, and then we'll evacuate to the northeast, which in this case is these coordinates. And then let's see what that looks like on the graph. So we're just computing the shortest route. The slow part here is the plotting, and here we go. Here is a graph of the optimal routes from that position that we cared about to the northeast, an evacuation scenario. And on this side, we're weighting based on the length, the geometric length. So I want to go the fewest number of miles or kilometers. And what's interesting then is that if you use the actual speed information encoded in this graph on the right side here, you'll see a very different route, right, outlined in blue as you go from this green dot to the red dot. And so this is important, right? Like this is a very different way if you want to optimize speed. You really want to know these travel time estimates. So clearly the optimal route changes drastically depending on if you care about distance or time. Something we can explore a little bit in greater detail, just with this final cell in this notebook, which is simply picking a random point, two random points in the graph and computing the optimal route. And since we have all this geographic information, right, we can actually plot the coordinates of the optimal route in this case, and then just explore. So this is what we get if we're going from green to red. Let's do it again just to explore. Again, this is something that you can experiment with if you want to try this on your own. Here's another example. Point here, right, is that once you have this pretty high fidelity graph, you can do a lot of routing pretty easily to show which is the optimal way to get from point A to point B. And hopefully, right, this is something that would be useful for a lot of different people, a lot of different use cases. So that is the notebook. Again, to run this is pretty quick. The slowest part is the actual deep learning piece. And again, that was only, in this case, about 16 minutes. So we showed how to do that. A few takeaways, right? Even with just a MacBook Pro, we're running at a 0.7 kilometers squared per minute. GPU inference would be much faster, clearly. And what's exciting, among other things, is that even for a city unseen during training, in this case, Dar es Salaam, the Cressy algorithm managed to return a routable road network, right? And this is true for all the top 5 winning space algorithms as well, right? So that was something that was something we really wanted to see if it worked, and it turns out it does work pretty well, which is pretty cool. just a few more screenshots. So this is pulling out the road network with the same methodology over Shanghai. And we're seeing a very high fidelity travel time extraction. I won't get into detail too much here, but there's a very low difference in apples time versus apples length scores, which means, again, we're pulling out this road speed quite well, which is exciting. Las Vegas is a much easier city to extract than others. So this is the prediction over Las Vegas, a pretty darn good road network. And kind of the final piece, right? Let's illustrate the different layers. So in this case, yellow is slower, and then we're building up a network. So red is fast. And this is something you can build with this algorithm that we've put out here. Final thoughts. The code's on GitHub, of course. We pulled it down for this demo, and then there's lots more information channels as well for those who are interested. Thanks for listening. Hope you guys all find this useful.